Hello everyone, and welcome back to the Kohi game engine series. Today we are going to tackle buffers. But before we do, I would like to take a quick second and thank the supporters of the channel, beginning with our partners, Eearslya, Wensheng, Caden, and Patrick. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. If you're interested in supporting the channel, you can find links in the description to YouTube memberships, as well as my Patreon page, which is patreon.com/Travis Vroman. So, buffers. Well, we've already talked about a couple of different kind of buffers. We've talked about command buffers, we've talked about frame buffers, but now I'm just saying buffers. What's the difference between this and some of these other buffers we've created? Right? Well, our command buffers, for example, hold commands to be executed, right? Whereas regular buffers in Vulkan just hold data. And so we have our meshes, eventually, that we are going to be rendering, right? So let's say we have a cube or a triangle, something like that. We need somewhere to actually hold that information so that Vulkan knows what to actually render, right? So we need a buffer to actually hold that data. More accurately, we actually need two buffers to hold that data. So we need one buffer to hold our vertex information. So right now that's our positions. And then we're going to need a second buffer to hold our what's called index information, because we render everything in triangles. I'm actually just going to make a quick crappy graphic here. So because we render everything in triangles, so let's say, for example, we wanted to render a quad, right? But the only thing that our GPU understands is triangles. Well, you might have already surmised that a quad is two triangles, which makes sense. So when you begin to think about this as two different triangles, so we have this first triangle here, which is composed of this point, and this point, right? And then we have the second triangle, which is here, which is composed of this point, and this point. And this makes sense, right? So if you had a list of these things to render out, you would have 6 vertices or 6 vertices with positional information to represent these things. However, if you think about it, we're actually wasting space by representing these two guys twice, because they're the exact same, right? And so if they are the same, well, why couldn't we just use them repeatedly? However, the way that geometry is actually typically stored is you might have them stored as, we'll say, number 0 here, 1, 2, and 3. And so these numbers here are just arbitrary. They could be stored in any order. It could go this way. It could go 0, 1, 2, 3. It could be any combination of these things, right? And so we need a way to reliably say, okay, I want the triangles for this, and then I want the vertices for this, and then I want the vertices for this. And so that is where the index comes into play, right? So let's say, for example, Blender output this with 4 of these vertices, right? Which is what we would ideally want instead of 6. Well, we'd want to register these things by these indices, right? So index 0 would be this one, 1 would be this one, 3 would be this one, 2 would be this one. And so when you actually go to render out this triangle, what you would actually be doing is rendering them by index. So for this first one, you would actually say 0, then 1, then 3, right? And then for the second one, you might say 3, then 1, then 2. And so these index numbers here are what is going to be stored in our index buffer. And I'm sorry about the crappy nature of this drawing, but hopefully it gets the point across. So we're going to have one buffer to actually store the x, y, z's of each one of these points, and then one to actually store the index buffer. And this is going to allow us to sort of deduplicate our geometry and just go by these individual indices and draw those instead of drawing each and every single individual point. Okay? So we automatically get to reuse 1 and 3 for both of these, even though they're actually only stored once. Okay? So to do that, we need, like I said before, we need 2 buffers, right? And so what I'm going to do is in our backend, at the top here, I'm going to create another function that's just going to be a private function called create buffers. And then I'm going to go all the way to the bottom, and we're going to, whoops, and we're going to define that. And what we're going to do is we're going to create a buffer structure that holds our buffers for us and call them using this. Okay? And so I'll go ahead and hook this up now so that we don't have to do that later. And so in our initialize, after we've created the shader, we'll just call create buffers and we'll pass context, right? And we'll need the address of that. Okay? And that way that is ready to go. And then down here we'll have to come back and destroy the buffers. Okay, so the first thing that we're going to want to do is we're going to need to define a type to actually hold our buffer. So that we're going to do in Vulkan types INL. Okay, and we'll keep this one towards the top. Okay, just above swap chain, create swap chain support info, right? And so I'm actually just going to paste in a structure. And this is what our Vulkan buffer is going to look like, right? It contains some information that we're going to need to evaluate things. So the main players here are this VK buffer, which we're going to call our handle. This is the actual Vulkan buffer that holds the data itself. We're going to need to hold our buffer usage. And we're also going to need to allocate and hold on to some device memory for this buffer. We are also going to indicate whether or not this buffer is locked. That'll make sense here in a little bit, as well as the type of memory and property flags that are associated with this memory here, as well as the total size of the buffer. Okay, so not too much there, but it's a structure that we need to simplify things a little bit. All right, so the next thing that we're going to need to do is we're going to need to create a new file under Vulkan. And we're going to call that vulkanbuffer.h. And as you might have guessed, we're going to pragma once and include Vulkan types. And we're going to have a relatively straightforward interface here. So we're going to have a create that takes the context, the size of the buffer, our memory, or our usage bits rather. So these are bit flags as to how the buffer will be used. The memory property flags, whether or not this buffer should be bound on create, because a buffer has to be bound in order to actually use it. And then a pointer to store the buffer that we create. Okay, and as you might have guessed, we are also going to have a destroy method for that buffer that takes the context and a pointer to the buffer. And next, we're actually going to need a way to load data into the buffer. And this is going to be done through something called locking and unlocking the memory within a buffer. And so when we get ready to fill these out, I will explain that more in depth. But this is basically going to be surrounding our loading of the data into the buffer, right? So speaking of which, we will have a Vulkan buffer load data. So our load data takes in the context, the pointer to the buffer, the offset from the beginning of the buffer that we're going to load into, the size of the data we're going to be loading, any flags that are relevant, and then a pointer to the data itself that's going to be loaded. So the order of this is going to be, we're going to lock the memory of the buffer, passing an offset, size, and flags. We'll load buffer into the data, and then we will unlock it. Okay? And that is going to cover most of our scenarios. We are also, however, going to need one additional thing. We won't, I don't think, need this right away, but we will need it, and it's just one more method, so we might as well go ahead and create it, which is a method to create or to copy data from one buffer to another. So that is just going to be our Vulkan buffer copy to. And this is the entire interface for our buffers. We will also, on second thoughts, we'll also need something to resize the buffer, which is basically going to recreate the buffer under the hood. We might as well go ahead and get that in here too, because there may be certain circumstances where a buffer isn't big enough, and we need to resize it, copy the data over, load it, so forth. Okay. All right. I believe. Let's see. Create, destroy, resize. I lied. There is actually one more thing. We also need the ability to bind the buffer, because you cannot use a buffer that is not bound. Okay. All right. Now we will create a new file, call it vulkanbuffer.c, and we will go ahead and we are going to include several files. So we need the Vulkan buffer, we need the device because we need to be able to get device memory. Some of these functions actually require some command buffer work, so we are going to create, so we're going to actually include that as well. We need Vulkan utils, and then we need logger and memory for memory management. Okay. So our first one is create. The first thing that we're going to do is we are going to zero the memory of our output buffer. Okay. And then we're going to set the total size, usage, and memory property flags on that buffer. So we're just basically copying those over at this point. As you might have guessed, we need a buffer create info because we're going to be creating a buffer. So that takes the size and the usage that we've passed in. And then our sharing mode is basically VK sharing mode exclusive. And this is an assumption that we're making that's pretty safe to make, that says that we're only going to be using this with one particular queue. So if we had a buffer that needed to be used across multiple queues, we would probably change this. But in our case, we don't really need that. So I'm going to make that assumption for now. And if we need the ability to adjust that, I can change it later. So next is just a simple call to VK create buffer. And we pass it all of the things that we need. So the device, logical device, the buffer info, which is this guy here, the allocator, as well as a pointer to the buffer handle. And then the next thing that we need to do is we need to gather memory requirements for that buffer, because remember, we actually don't automatically get the memory that we need for that buffer. We actually have to tell Vulkan how much memory we need, what type, and so forth. So we're going to get the buffer memory requirements here by calling vk get buffer memory requirements, and that populates this structure here. So we'll go ahead and set the memory index here to what we return from context find memory index, and we'll pass along the memory type bits from the requirements as well as any property flags that we have passed along. And if this returns -1, meaning we did not find the appropriate type of memory, then we will go ahead and abort at this case and return false after throwing an error. Next, we will need to allocate the memory. So you guys have probably seen this before. So you guys have seen this memory allocation before. We are just going to fill out the allocation size and the memory type index that we retrieve here. Now we'll go ahead and actually allocate the memory. So we just call vk allocate memory, pass along all the things that we have set up thus far. Verify that it was successful, and if not, we go ahead and throw an error about it and return false. And then if we actually passed bind on create, then we go ahead and call Vulkan buffer bind right off the bat. And this, by default, sets the offset to 0, so it binds it from the very beginning. If you don't want to do that, then you would pass this as false and bind manually. Okay, and then obviously at this point, if we've gotten this far, everything's been successful and we can return true. Destruction is pretty straightforward, so I'm not going to go through that step by step. We basically free the memory, destroy the buffer, and then zero stuff out. Buffer resize is basically going to be creating the new buffer, right? Which you might expect, because we can't resize a buffer, it's immutable. So what we're going to do is we're going to create a new buffer, and then after we have created it, we will go ahead and gather memory requirements for it, right? So there we go. And then we'll go ahead and allocate memory info for it. Okay, allocate the memory. Okay. Then we're going to bind the new buffer's memory. Okay. And then we are going to copy over the data. So we are going to copy our Vulkan buffer copy 2. And basically we're going to say that we're going to copy from the buffer that we passed in to the new buffer handle. Okay, and with offsets of 0. So we're going to copy the whole thing. And then we will do a VK device wait idle to make sure that anything potentially using it is finished. And then we are going to destroy the old buffer, right? So we're going to destroy the buffer memory and the buffer handle. And then we will set the new total size, memory, and handle for the new buffer that we created and return true, right? So it's actually, it looks like a lot of code, but it's not actually doing that much, okay? Binding the buffer is just a one-line call. So all that is a call to VK bind buffer memory, which we actually already did here. So it's basically the same thing. The only difference is you can provide an offset. Okay. All right. So the next thing is locking memory. So this is basically saying we want to map the memory to this void pointer here, right? So we're basically going to say we want to take whatever is stored in this buffer and map the buffer's memory to this block of memory right here. So this actually sets up a block of memory for us under the hood and outputs that here. And then we can return that as a void pointer. So this basically says take whatever is currently allocated to this buffer and map it to a void pointer that we can then return. And then unlock essentially does the opposite, where it unmaps that memory. And then that buffer's memory that is mapped, or the pointer that was obtained from this, is no longer valid at that point. Okay. So Vulkan buffer load data basically performs these two things and automatically copies the memory over for you. So if you wanted to handle this separately, you could call these. If you want to do this all in one step, you could do this. So this maps the memory to a local pointer, copies everything in data over to that pointer, and then unmaps it. So you're essentially copying into the buffer's memory by doing this. So it's basically this step and this step with the copy in between automatically handled for you. So it's just a little bit of a convenience thing there. Okay, and finally the copy 2, which is actually not very complicated either. So the first thing that we're going to do is we're going to wait for the passed in queue to be idle, because this requires a command buffer and a queue. We are going to create a one-time use command buffer. So if you guys recall, we actually did a lot of logic around this. So this is an example of what we would use a one-time use command buffer for, is just a quick copy operation. And so we will set up a VK buffer copy, which basically says our source offset and our destination offset and the overall size of the copy operation. And then we call VK command copy buffer against the temporary command buffer that we've created here. We pass in the source buffer, the destination buffer. We're going to copy 1 unit of this, And then here is our copy region that we passed in. We just treat that as an array by passing the address of it. All right, so here we just submit the buffer for execution and wait for it to complete. Okay. And that is all there is to Vulkan buffers, right? We probably will come in here and add some more stuff to it in the future, but that's really all there is to it. It's pretty straightforward stuff. So now in our Vulkan backend, we can go ahead and create our buffers. So the first thing we're going to need to do is go into context. And we're actually going to need to add some storage for our buffers here. So I'm going to add this right underneath main render pass. And we're going to have a object vertex buffer and an object index buffer. Okay, and we're going to have different buffers probably for the different types of objects, right? So for now, I'm just going to create these as object vertex and object index buffers. Okay. And so back here, we can go ahead and create each one of these buffers. So the first thing that we're going to want to do is set up some memory property flag bits. And this is basically saying that the type of memory that we want to use is local to the device. So we do not want to use host coherent or host visible memory because it's much faster for the graphics card to access the device if it's device local. Okay. And I will get into how we actually upload that in a bit. So the first thing that we want to do is create the vertex buffer. That's going to be the size of vertex 3D, which we do not have. So we will need to include math types. And I had a comment there that says 64 megabytes, which is actually what this is going to wind up being once we create, once we fill out this vertex 3D structure, but I'm going to remove that for now because it's not accurate. So basically it's going to be the size of a vertex 3D times 1024 times 1024, which is going to give us plenty of space to work with. Okay. And next we're actually going to go ahead and call the create on that. Okay. And so what we're going to pass to that is the context, the vertex buffer size, and then the usage, which is going to say we're going to use this as the vertex buffer. We are going to set this up both to be usable as a source and a destination for transfers. And then we are going to pass through our memory property flags here. And then of course we want to bind it right away, and we want to store this in the context object vertex buffer. Okay. And it just occurred to me that I haven't actually used this file or included this file, so we need the Vulkan buffer included. So we'll include vulkan buffer.h. All right. And then one other thing that we're going to need to create is in our context, we are going to need what I'm going to call a geometry vertex offset and a geometry index offset. And this is going to be the offset that we're going to maintain. It's just a running offset that we're going to maintain every time we load data into the buffer. So that way we don't sort of overwrite our data as we go. And we'll have something that's far more advanced than this for our final allocation routine, but for right now, this is just nice and simple to get something up and running. Okay, and so we are going to start off by setting that to 0, right? And now we're actually going to set up the index buffer. Whoops. So we are going to start off by setting that to 0. And now we're going to set up the index buffer. And of course we are going to call create. And we are going to set the running index offset to 0 as well. And then we're just going to return true. Okay. And that really should be it in terms of creating the buffers. The only other thing you'll need to do here is destroy our buffers. So let's go ahead and build. and we'll run. And we see that our application created successfully, and we can close, and there are no errors. So that is going to do it. Next, we are going to start looking at the uploading of geometry, and from there we can actually start rendering stuff. So we're getting very, very close. Thank you guys so much for following along. I hope you've enjoyed this series so far. I hope you've learned. If you liked the video, please toss it a thumbs up. If you haven't already, consider subscribing. Click the little bell icon there to get notifications as to when new videos in this or other series drops, and I will see you guys next time.